Welcome to the class. We will continue our discussion about blade design and cascade theory. Till time what we had seen was the cascade tunnel, parts of cascade tunnel, and then we had seen about the turbine cascade, different angles of the turbine cascade. Now we will go ahead and talk about velocity triangle in turbine cascade. We will take a control volume in a turbine cascade which includes aerofoils, sections for two nearby blades, and then this we will use for our further analysis. So, this is our control volume. Now, which includes one pitch at least. So, this is turbine cascade, and now this is control volume. Now, this is spacing between the blades, and then this what we call as the pitch S, and here we have velocity absolute approaching like this, which is C1. So, this is Cx1 and then this is Cy1 approaching at an angle alpha 1. We have seen these are the alpha 1 and alpha 2 are the air angles at inlet and outlet. So, these are the angles made by the absolute velocity with axial direction. So, similarly, this is absolute velocity C2 leaving the blade, then this is alpha 2 since this is Cx2 and this is Cy2. Here from these two velocity triangles a mean velocity triangle is constructed. So, this is Cxm and then this is Cm and this is Cym, and the angle included is alpha m. In such case the forces acting are, this is Fy, this is Fx, and hence the resultant is Fr. But this resultant can further be decomposed into two more components which are lift and drag. So, for that these components will be made which are normal and perpendicular to the velocity, so mean velocity. So, this is lift and this is drag. So, this total force Fr actually gets decomposed into two ways. One is Fx Fy, which has the coordinate system associated with laboratory coordinate system, and then it gets further decomposed into two more components which are lift and drag, which are normal to the velocity, which are based upon the velocity direction. So, this angle this included angle is alpha m. Now, having said this, we will write down the expressions. So, Cxm, which is axial mean velocity, is half of Cx1 plus Cx2. Cym, since yms are in opposite direction, we will have Cy2 minus Cy1, and tan alpha m is equal to Cym divided by Cxm, and then we have for constant axial velocity we have tan of alpha m is equal to half of tan of alpha 2 minus tan of alpha 1. So, this is for the case of constant axial velocity. So, now having these control volume with us, we will go ahead and find out what are the forces acting on the cascade. So, let us apply mass conservation or continuity equation. And in the continuity equation we have m dot is equal to rho 1 Cx1 into S is the pitch into 1 is the blade height, and we are considering it to be unit. So, similarly we have rho 2 Cx2 into S into 1 for incompressible flow. We have rho 1 is equal to rho 2 is equal to rho. So, we have m dot is equal to rho Cx1s is equal to rho Cx2s. So, we have x1 Cx1 is equal to Cx2 is equal to Cxm. So, m dot is equal to rho Cxm into S. Now, let us apply y momentum equation, or let us apply momentum equation in y direction. Here by this we can write the force Fy will have its magnitude as m dot into Cy2 minus Cy1 minus. So, this is Fy. So, what we will have is Fy is equal to m dot into Cy2 plus Cy1. We can put the expression for m dot rho Cxm s into Cy2 plus Cy1. From the triangle we can write down Cy2 is equal to Cx1 into tan of alpha 1. So, it is equal to Cxm into tan of alpha 1. Similarly, Cy2 is equal to Cx2 tan of alpha 2 is equal to Cx1 into tan of alpha 1. So, putting this in the expression for momentum, we can get Fy is equal to rho Cxm into S into Cxm tan of alpha 1 plus Cxm into tan of alpha 2. So, Fy is equal to rho Cxm square into S into tan alpha 1 plus tan of alpha 2. We can rearrange the term and write down as half rho L Cxm square into 2 into S by L into tan of alpha 1 plus tan of alpha 2. We are purposely doing, since we can write down this coefficient of force Cfy is equal to Fy divided by half rho L Cxm square, and then this gives us answer as 2 into S by L into tan of alpha 1 plus tan of alpha 2. So, if we know alpha 1 and alpha 2 for given geometry and arrangement, we can find out what is the coefficient of the normal force which is acting on the blades. Then we can write down the momentum equation. in x direction. So we will have Fx is equal to, here we just would not have forces, momentum change equal to force, we will have pressure change as well. So P1 minus P2 is the change in pressure in the direction of flow, which is S into 1 is the area plus rho into S into 1 for unit blade height Cxm into Cx1 minus Cx2. So we have for incompressible flow we can write down P1 is equal to P01 minus half rho into C1 square. Basically this expression says that P01 is equal to P1 plus half rho V square. This is strictly for incompressible flows where total pressure is equal to static plus dynamic pressures. So we are finding out static pressure from the total pressure and the dynamic pressure after subtracting them. Similarly, we can write down P2 is equal to P02 minus half rho to C2 square. So we can write P1 minus P2 is equal to P01 minus P02 plus half C2 square minus C1 square into rho. So we can write down expression for Fx. We can write down expression for Fx again P1 minus P2 into S plus rho into S into Cxm into Cx1 minus Cx2. Take a particular case where we have if Cx1 is equal to Cx2, we can write down Fx only as P1 minus P2 into S. So Fx is equal to P01 minus P02 into S plus half rho S into C2 square minus C1 square. We can write down the same expression Fx is equal to S into delta P naught plus half rho S into C2 square minus C1 square. Here we know that C2 square is equal to Cx square plus Cy square and C1 square is equal to Cx square plus Cy square. So Fx is equal to S delta P naught plus rho into S. Now we will have basically Cx2 square plus Cy2 square minus Cx1 square minus Cy1 square, and both being equal it would get cancelled. So Fx is equal to S delta P naught plus half rho S into Cy2 square minus Cy1 square. But from velocity triangle we can write down Cy2 is equal to Cx2 into tan of alpha 2, which is equal to Cxm into tan of alpha 2. Similarly, Cy1 is equal to C1 tan alpha 1, which is equal to Cxm tan of alpha 1. So Fx is equal to S delta P naught into half rho S into Cy2 square, which is Cxm square tan square alpha 2 minus Cxm square tan square alpha 1. So, we will have Fx is equal to S delta P naught plus half rho S Cxm square into tan square alpha 2 minus tan square alpha 1. So, Fx is equal to S delta P naught, we can write down it as rho S Cxm square into tan alpha 2 minus tan alpha 1 into tan of alpha 2 plus tan of alpha 1. These are the two expressions for us. Further, we know half into this term can lead to tan of alpha xm. So, we can write down it as del S delta P naught plus rho S delta xm into tan of alpha m into tan alpha 2 plus tan alpha 1. We will remember this expression and we will name it as number 1 and we will name it as number 2. So, we can write down Cfx is equal to Fx upon half rho L Cx m square, and this gives us, if we use equation number 1, we can get S delta P naught divided by half rho L xm square plus half rho xm square will cancel and we will have S by L into tan of tan square alpha 2 minus tan square alpha 1. So, this is our non-dimensional form of axial force coefficient. Having said this, we can move ahead and find out what is lift and drag from the coefficients whatever we have got or from the forces whatever we have arrived at. So, L lift from the force, resultant force and its decomposition, we can clearly mention a lift is equal to Fy cos of alpha m plus Fx sin of alpha m. So, L is equal to Fy we have found out, Fx we have found out, we can keep those expressions written over here, rho S Cxm square into tan of alpha 1 plus tan of alpha 2 into cos of alpha xm plus rho S Cxm square into tan of alpha xm into tan of alpha 1 plus tan of alpha 2 into sin alpha m plus S delta P naught into sin of alpha m. Now, here we can rearrange and then we can take rho x m rho S xm square into tan alpha 1 plus alpha 2 common from first two terms of this, and then we can have rho S Cxm square into tan of alpha 1 plus tan of alpha 2 into, we will have cos of alpha m plus sin square. So, we have tan alpha m into sin alpha m. So, tan alpha m is equal to sin alpha m upon cos alpha m. So, we will have it is sin square alpha m upon cos alpha m plus S delta P naught sin alpha m. Now we can take alpha m also common from this bracket, and then we have L is equal to rho S Cxm square into cos alpha m, and then we will have tan alpha 1 plus tan alpha 2. So, we would have taken alpha 1 cos alpha 1 common, it will become tan square alpha m plus S delta p naught sin alpha m. So, L, but we know 1 plus tan square alpha is equal to sec square alpha. So, here we will have sec square alpha m, but we have one more cos alpha m here. So, that is a reciprocal. So, we can write it as rho S Cxm square into only one sec alpha m into tan alpha 1 plus tan alpha 2 plus S delta p naught sin of alpha m. So, this is our expression for the lift. Okay. So, we can write down CL, which is lift coefficient, as L half rho L Cxm square, and then we can get it as S half, we will get 2, we will get 2 into rho into S by L into sec alpha m into tan alpha 1 plus tan alpha 2 plus S delta p naught half rho L Cxm square into sin of alpha m. So, knowing this way, we can find out what is the lift coefficient which is getting acted on the cascade, which is a turbine cascade. Now, we will move ahead and then we can find out drag force for the turbine cascade. So, for drag force, again from the force resultant force and its decomposition, we can write down d, which is drag, which is equal to Fx cos of alpha m minus Fy sin of alpha m. So, we have d, we can put the expression for Fx as rho S Cxm square into tan of alpha m into tan alpha 1 plus tan alpha 2 into cos of alpha m minus, this is rather plus S delta p naught into cos alpha m minus rho S Cxm square into tan alpha 1 plus tan alpha 2 into sin alpha m. Here it is good point to note that we have tan alpha m and cos alpha m. So, this would ultimately be sin alpha m. So, we can see that the first term and the third term, they are same. So, drag is equal to S delta p naught cos of alpha m. So, we can get drag coefficient as drag divided by half rho L Cxm square is equal to S delta p naught cos alpha m into half rho L Cxm square. Now, this is how we would have found out different coefficients and the forces which are acting on the cascade, and we can see over here that everything depends upon the setting of the angle and the blade angles and the angles whatever we would have used for the blade, for the air and also for the setting. So, we will move ahead for the compressor cascade. And we can note that for the compressor cascade, first it will be same wind tunnel, which is the cascade tunnel getting applied for the application of the compressor. So, we will change our turbine cascade to the compressor cascade in case of compressors. So, this is the C1. So, this will be CX1, this will be CY1, so this will be CX2, this will be CY2, and then this will be C2. On a particular aerofoil, if we plot the velocity distribution, then this velocity distribution for x by L can be seen like this. This is a typical velocity distribution for suction side on top and for pressure side on bottom, pressure side. Now again we will draw the angles for the cascade, which is a compressor cascade, as what we did earlier. In case of turbine, we drew three types of angles. First angle was Kimber angle. So, for Kimber angle, so this is Kimber line. So, this is the vertical line. So, this is the tangent to the camber at the inlet. So, this is chi1. And this is chi2. Basically, this vertical line is the chord line in this specific case. So, this is chi2. So, this is Kimber angle, as what we had seen earlier. This is chi1 and chi2, they are the angles between tangents to camber line and chord line. Then we will show the blade angles. So, for the blade angle, we will make the chord little bit tilted. So, now this is chord, and now this is camber line, and now this is tangent to the camber. So, as what we know, this angle is chi1, and this is, we will put it here, chi2. Now, I will plot the axial direction here, and then we will have the tangent and the axial direction. We will have angle alpha 1 dash. So, similarly here also it is alpha 2 dash. So this is blade angle. Which are alpha 1 dash and alpha 2 dash, angles between axial direction and tangent to Kimber line. And then we can have third, which is for air angle. So same way we will replicate this is camber line and this is axial direction, and this is suppose the direction of velocity, which is c1. So this angle is alpha 1. Similarly, if velocity is leaving, absolute velocity in this direction, and this is alpha 2, this is the axial direction. So we have air angles which are alpha 1 comma alpha 2. So they are angles between absolute velocity and axial direction. So having said this, we can continue here showing the other angles. Among that, first was the stagger angle, and stagger angle can be shown over here. This gamma will be the stagger angle, which is between the chord line and the axial direction. So other settings we can easily make out as what we did earlier. Kimber angle theta is equal to chi 1 plus chi 2, which is alpha 1 dash minus alpha 2 dash. Further, alpha 1 dash is equal to chi 1 plus gamma, and alpha 2 dash is equal to gamma minus chi 2. It should be noted here that this angle, which is between the tangent, which is between the, so this big angle is gamma in the outside, in the outlet. So this gamma is equal to, this gamma minus chi 2 is alpha 2 dash. So we can write down alpha 1 dash minus alpha 2 dash is equal to chi 1 plus chi 2, which is theta. So I we have defined as incidence angle. So it is alpha 1 minus alpha 1 dash. We have defined delta, which is deviation angle, and then that is alpha 2 minus alpha 2 dash. So we have epsilon, which is deflection angle, and then that is alpha 1 minus alpha 2. So epsilon is equal to alpha 1 dash plus I. From the expression of this, alpha 1 dash plus I minus alpha 2 dash plus delta. So deflection is alpha 1 dash minus alpha 2 dash plus I minus delta, but alpha 1 dash minus alpha 2 dash is equal to theta. So it is theta plus I minus delta. This is the deflection angle. So now for the compressor cascade we can again plot the velocity triangle. So velocity triangle for compressor cascade, here as well we will draw a control volume. So for that let us first plot the aerofoil. And let us complete the control volume. So this is the control volume for the compressor cascade. So here we will say this is P01 and P1 and this is P2 and P02, since this is inlet. So for the inlet we know that this is the direction of absolute velocity, this is direction of axial velocity. So this is Cy1. Similarly, if we take outlet, then for outlet this is C2, this is Cx2 and this is Cy2. So we can draw the mean velocity triangle as Cxm, this is Cm and this is Cym, and this angle mean is alpha m. So this is the typical velocity triangle for compressor cascade. Now we can show the forces same way as what we did for turbine. This is Fy, this is Fx. So this becomes the resultant Fr. Now here we again need to decompose them into lift and drag. So this is lift and this is drag. And this resultant is Fr. So we can continue by applying momentum equations for the compressor cascade. So let us apply mass first. Mass conservation. Here we get m dot is equal to rho Cx1 S into 1. We know at the outlet rho 2 Cx2 into S into 1 for unit blade height, but again we will say that Cx1 is equal to Cx2 is equal to Cxm. For the constant axial velocity we can get it as rho Cxm into S, where we are saying it as incompressible, which has led to rho 1 is equal to rho 2 equal to rho, and then we have said Cx1 is equal to Cx2 is equal to Cxm. So this is how we would have the mass conservation equation for compressor cascade, which is same as what for the turbine cascade. Now let us apply tangential or y momentum equation. If we apply, we can get Fy is equal to m dot into Cy1 minus Cy2. Here it should be remembered that both y components are in the same direction, which was in the case of turbine both were in opposing. So we had Cy1 plus Cy2. So we can write down, put m dot, expression for m dot rho Cxms into Cy1 minus Cy2. So, we will have Fy is equal to rho Cxm into S. We can put Cy as Cxm into tan alpha 1 minus Cxm into tan alpha 2. So, Fy is equal to rho Cxm square into S into tan alpha 1 minus tan alpha 2. So, we can write down coefficient of force Fy, which is Fy divided by half rho L Cxm square is equal to 2 into S by L into tan alpha 1 minus tan alpha 2. Similarly, we can apply the axial momentum equation or x momentum equation. There we can write down Fx is equal to P2 minus P1 into S into 1 plus rho S into Cxm into Cx2 minus Cx1. But again we would have same axial velocities. So, Fx is equal to P2 minus P1. We already know that P2 is equal to P02 minus half rho C2 square minus P01 minus half rho C1 square into S. Here we can mention Fx as half rho S C1 square minus C2 square minus delta P naught. So, delta P naught is P naught 1 minus P naught 2 over here, since we have minus sign here. So, Fx can be written as the half rho S. So, C1 square can be split into 2, Cx1 square plus Cy1 square. Similarly, C2 square will also be split into Cx1 square plus Cx2 square plus Cy2 square plus Cx and Cx1 and Cyx2 both are equal. So, we will have only y2 remaining. So, Cy1 square minus Cy2 square minus delta P naught into S. We can put the value of Cy using the velocity triangle as Cxm square into tan alpha 1 square minus Cxm square into tan alpha 2 square minus delta P naught S. So, Fx is equal to half rho S Cxm square into tan square alpha 1 minus tan square alpha 2 minus delta P naught into S. Similarly, we can decompose, we can keep this equation 1 remembered, we can decompose the bracket and then write Cxm square half rho S into tan of alpha 1 plus tan of alpha 2 into tan of alpha 1 minus tan of alpha 2 minus delta P naught into S. So, Fx we can make this half and this bracket, and then we can have rho S Cxm square, and this will get replaced by tan alpha m, and then this will be tan alpha 1 minus tan alpha 2 minus S into delta P naught. So we can write down force coefficient in x direction as Fx divided by half rho L Cxm square, and then we will get it as, if we use this expression, this we will remember as 2, and then we can get it as S by L into tan of tan square alpha 1 minus tan square alpha 2 minus S delta P naught half rho L Cxm square. Now, having this force coefficient in axial direction known and similarly force coefficient in normal direction known, we can find out lift and drag. So, lift L is equal to, from the decomposition of forces, Fy cos alpha m plus Fx sin alpha m. So, lift from the Fy expression rho s Cxm square into cos alpha m into tan alpha 1 minus tan alpha 2 plus rho s Cxm square into tan alpha 1 minus tan alpha 2 into tan alpha m into sin alpha m minus S delta P naught into sin alpha m. So, L is equal to, we can take this common from both the terms, and then we can write down rho s Cxm square into tan alpha 1 minus tan alpha 2, then we will have cos alpha m plus sin square alpha m divided by cos alpha m. Here we have two terms. These two terms mean this single term, which is sin alpha m divided by cos alpha m. So, S delta P naught into sin alpha m. So, we have rho S Cxm square into tan alpha 1 minus tan alpha 2. We can still take cos alpha m common. Once we take cos alpha m common, we know it will decompose into tan square 1 plus tan square alpha m minus S delta P naught sin alpha m. So, we can say that rho s Cxm square tan alpha 1 minus tan alpha 2. So, this cos alpha m and then this term is sec square alpha m. So, we will have sec alpha m minus S delta P naught sin alpha m. So, we can write down L as this, and hence we can further say that we can further find out the lift coefficient as lift divided by half rho L Cxm square, and then we can have it as 2 into S by L. Rho Cxm will get cancelled, then we have tan alpha 1 minus tan alpha 2 into sec alpha m minus S delta P naught half rho L Cxm square into sin alpha m. So, this is the expression for lift coefficient. Now, we can find out drag. So, drag from the decomposition of force is same Fy sin alpha m minus Fx cos alpha m. So, we can put the expression for Fy rho s Cxm square into tan alpha m 1 minus tan alpha 2 into sin alpha m minus rho s Cxm square into tan alpha 1 minus tan alpha 2 into tan alpha m into cos alpha m plus s delta p naught into cos alpha m. So, we have d is equal to rho s Cxm square into tan alpha 1 minus tan alpha 2 into sin alpha m in minus rho s Cxm square into tan alpha 1 minus tan alpha 2, and these two terms combinedly will make sin alpha m. So, we will have s delta p naught cos alpha m. We can see that the first two terms are same. So, we have drag is equal to s delta p naught cos of alpha m. So, we can write down drag coefficient CD is equal to drag divided by half rho L Cxm square. So, it is S delta p naught cos alpha m divided by half rho L Cxm square. So, this is the method by which we can find out the different forces acting on the cascade. So, here what we have seen that what are the different angles associated with a cascade testing or blade design or blade testing, the angles like Kimber angle, air angle, blade angle. So, these are the angles, and once we set these angles, we measure the direction of velocities and we can get the drag forces acting on the drag and lift or the Fx and Fy forces acting on the cascade. So, having said this, we have talked about the complete blade design and cascade tunnel and the flow through a cascade. Here we have completed the portion which is related with the blade design and cascade theory. Thank you.